Okay, it's time to get started. Welcome back. And today we're going to do two lectures. We're going to do Lecture 5 and Lecture 6. Today's focus, we've covered requirements, we've covered analysis and concept. Now what we're going to look at is the nitty-gritty details of what it means to perform the analysis. One of the things you're going to have to do for your analysis document is to create two diagrams. One's going to be an entity relationship. The other one is going to be a data flow diagram. So Lecture 5 is on everything you need to know about entity relationship diagramming, and Lecture 6 obviously is on data flow diagramming. So this is probably important lectures to keep in mind, and now you can go back and read it again if you want, or listen to the video again if you miss a concept, because I'm going to kind of go through it on a fast side, but assuming some of you may have heard about this stuff already if you've taken my database class. You probably heard about entity relationship modeling, but you may not have heard about data flow diagramming. So it gives you an opportunity to kind of and I'll say some different things because I'll be relating this to software engineering and not building databases. So I'll give you slightly more information or different information than I gave you if you've listened to this already. And plus this is a different lecture as well. So let's talk about the concept of entity relationship modeling. Actually, just by show of hands, is anyone familiar with this already? You are? You are. Y'all took the database class? No? You're just familiar with it? Have you done this in practice? No? Okay, good. And where did you hear about it?
In my bachelor days when I did my computer.
Oh, okay. Yeah, this was applied at a graduate level, applied to development of a project. So you'll have to actually take the model itself and use it with your project. So what you're going to be doing, and which actually kind of leads into a good segment here, for your project, you'll be creating at least one entity relationship diagram. And what you're going to end up doing is diagramming some component of the system. You cannot diagram the entire system with this diagram. This is only showing you basic components in terms of logical structure. Entities are like objects. And for those of you who haven't had any exposure, because I got like 50-50 on the hands, so some of you have had it, some of you haven't. So I have to go through everything. So if I had 100%, I could skip this lecture completely, I guess. But then we would go home early today. So anyway, but let's get back to the concept. So entities are like objects in the real world. Object is a person, place, or thing, or concept. And the technique, what we're doing is we're applying it now. If you've had this lecture before in database class, it was all about building the architecture for the database. It told us that the end diagram told us what tables to create, and there was rules to follow. So we created the diagram, we traversed the diagram or read the diagram, and then we created a list of tables from that, and multiple valued relationships turned into tables, some of the entities or most of the entities turned into tables, and it was used as a methodology to decide the structure of the database. Now we're going to use the same concept, but we're going to apply it to a software engineering project, and we're going to describe the entire system. So going back to the different types of diagrams that exist, this would be a process-oriented diagram, showing the logical structure. So it fits into both logical structure and process. And what we're looking at is the conceptual or logical design of the system. And it's widely accepted as a modeling approach. There's three notations on the diagram, as the slide you've been staring at is telling you: entities, attributes, and relationships. When you start creating them for software projects, don't think about databases. One of the problems a lot of people do is they think, oh, we're designing the database. No, in this case you're designing the system. So we're not going to break this out into tables. So we don't actually have to cover that part either, because we're not going to essentially create anything from this. We're using it to understand the structure of the system. We can take the entity relationship diagram and turn it into two object-oriented diagrams with a direct translation. It turns into both the object diagram and it turns into the class diagram, because they're both one and the same. Well, they're showing different levels of detail, which goes back to the concept of diagramming, and what we're trying to achieve here is look at the system from a couple of different levels of abstraction and understand it from a lot of different viewpoints. And one of them, in terms of entities, falls in nicely with object orientation, which is why people still kind of lean towards this direction. So what's an entity? An entity is an object that can be identified in the user's work environment. So now you're thinking, well, I thought we were modeling software. We are, but we're actually modeling the real world. So we're taking the work environment and modeling it from an outside the system perspective. We're not looking at the functionality of the system. And for people who have never had this before, they start looking at this going, well, how do we model? And I don't know what to put in this model. And then you realize you can't put the entire system in the model sometimes. Sometimes you have to actually create more than one diagram to get the entire system actually built from these components. So let's talk about entities. It's a thing or object in the real world within the application context. Entity has a set of properties which uniquely identifies it. Kind of sounds like an object. Entity is presented in a rectangular form. So here we have an entity in the ER diagram called project as an example, and it's just a rectangle you see on the bottom of the screen. So you want to use a rectangle. So what's an attribute? Okay, now how many people are familiar with object orientation? Raise hands. You guys are, because you took the object-oriented programming Java class. It looks like 50-50. This is actually kind of a different set of group. But you guys were in the database class too, weren't you? Yeah, so you had this already as well. Lo and behold, here it is again. Different perspective, though. Not quite as much detail either. This is 20 slides, everything you ever wanted to know about entity relationship. There we spent like 2 weeks or 3 weeks on it. So, all right, an attribute is a quality or characteristic. The database people are thinking, yeah, it's a column in the database table. It is, however, it's also a piece of information. It is data that's being stored. So attributes turn into the data. If you think about, take databases out of the picture and say, we're going to model this using object orientation. Or we're going to model this, because some of the people know object orientation, so I can use those terms now. Or we're going to model this using a systems analysis and design approach. What kind of data are we storing about each one of the individual entities or objects in the system? It helps us generate a list, and those would be considered the attributes. And then we also have behaviors in object world, but we don't have that in entity world. So that's why the entity relationship diagram isn't the exact equivalent to the object diagram or the class diagram. It's an approach to take you there in an easy couple of easy steps, essentially. It translates quite well, but there is a translation that has to occur. So back to the concept of the attribute as an example for an employee. Some of them might be name, extension, data hire, stuff like that. Common to see attributes with bubbles. Then along came object orientation, and people said, no, let's put it inside the box. It makes it look like a class, actually, at that point. Because the class box, and this is the box here that would represent the object or the class. Inside of it, you see the attributes normally in modern day kind of diagramming. But you still see kind of this. And in systems programming, in development, sometimes you do see this because this is easier for the user to understand. It's like, this project name, location, budget, they're all part project. So it makes it kind of easier. So represented in ellipses, as in the ER diagram itself. And up here on the top would be if we were to take this particular item and turn it into, because we're looking at the data, if we're looking into a table, we say, if we had a project table, these are the columns that we would have in the table. So if you can actually kind of think of it in terms of database terms. And the reason why this diagramming method is very popular is because this is usually translated to the database, although it doesn't have to be. You can create this for a program that doesn't use a database. So we have this concept of relationships, and there are associations between the entities that are expressed by real-world relationships, hopefully. So the project employs employees, and so we have the project and the employee that participate in the employees relationship. So what you're doing with your project statement is you're going through your requirements specification, pulling it out line by line, and say, well, the projects, they employ employees, or we have employees that work for projects. And this particular application is tracking these employees that are working with these projects or something. So you draw this out. You'd say, here's how it looks. Some of you are looking at me, well, why don't I draw it out for? And some people think, oh, that's a lot of extra work. We don't really have to do that. The thing is, when you see it on paper, then you start seeing what you're missing. You say, it's not necessarily what it is and yeah, I know that. Why am I drawing it out? Because once you put what you know on the paper, then you see what you don't know. Because then you start saying, oh, wait a minute, something's missing. What about the bosses for the employees? What about and then all of a sudden it helps you understand what it is you're building, and then you go back and fix the requirements, essentially, is what ends up at this point. Because you're doing analysis. It's part of the analysis exercises to create this diagram. So here we have the project, the employees that participate in the employee's relationship, the function of the entity plays in the entity. Relationship is called the entity's role. And I've purposely switched the terminology in this lecture with object-oriented terminology. Because in software engineering, outside of databases, we see roles. We see full and partial participation, we see roles, and we see associations. That's all UML terms, which is not traditionally systems analysis and design, but it's the same thing, it's just different terminology. So we actually do have roles in terms of the participation. And then we have sets of relationships. So what we're doing in terms of the diagramming is coming up with multiple sets. And so in your analysis document, the requirement is to create one entity relationship diagram. If you could actually create one that showed everything about your system, unless your system is like a calculator program, actually I don't think you could put a calculator program in one either. Maybe it's Notepad. No, I don't think you can do a Notepad either. Rarely can you get an application that actually has just one entity relationship diagram out of it. Normally you have 3 to 5 diagrams that come out of that. Because in order to really model the entire system, and think of the concept, you're not modeling the database anymore. You're modeling the system from a logical structure. The system that's going to take a year and a half to build is going to have more than one. But for your project, you're only required to do one. Here's the trick, however. The more you do in the analysis, the easier your design ends up being. We have 2 deliverables in the course. We have the analysis document that doesn't exist in the real world, and then we have the design document. The analysis is the rough draft to the design. Analysis doesn't have as many requirements. Their design has more requirements. So what you're doing is all the work for the design. A lot of students like to flip ahead, look at the design, and start working on that, and then turn in partial for the, just pull out one of those, put it in here for the analysis. Pull out one of those, put it in. If you just make one entity relationship diagram and you stop there, you have more work ahead of you on the design. So the more work you put into the analysis, the less work you have to do. Some students can actually just add a few things to it, change the label, call it the design, and they're done, essentially, outside of the prototype. So, long story short, the more analysis work you do, the easier the design comes, which is kind of like what happens in the real world. If you spend 2 months analyzing it, the design happens in a week. If you don't spend any time at all analyzing it, the design takes 3 or 4 weeks, and then it's not really complete. It's kind of like how many drafts of a paper are you going to write? First draft is never going to be the final draft, hopefully, unless you are a college student. Then it ends up being the final draft. All right, so here's some relationship set examples. There can be more than one relationship between the entities. Here we have the road and we have the town. We have 2 different relationships, so we can show multiple relationships. And all you're doing for these diagrams is drawing diamond symbols for the relationships and rectangle symbols to represent the entities. And you're drawing lines between them. These are examples, and for the purposes of this course, you're not graded on the quality of the diagram in terms of your artistic ability, or in terms of the tool that you're using, or in terms of the correctness. It's a learning process, different than the database class. The database class, you were judged primarily on, was the diagram correct? Was it actually showing what it's supposed to be showing? Here, you're doing this to understand it. So obviously, there might be different revisions. What ends up happening is, just like writing a paper, the first diagram is not really the final diagram. It's the first draft of the diagram. So some people come up with better quality diagrams than others, just naturally, especially if you've had more experience doing this. But overall, the diagram, whether it's correct or not, you figure it out, and then you make a note and say, oh, this diagram's not really correct. But this part of it is. And you could still use it in the documentation, but you have to note that there's something wrong with the diagram. A good team would, with a lot of time, would go back and fix the diagram eventually. So. And when I say good, I mean clear. Make it clear. Because what ends up happening is you store this stuff, and then 20 years from now, well, maybe not 20 years, 5 years from now, the project team, a different team comes back and looks at this, says, well, these are the diagrams. Oh, look at that. This is how the system was composed. You know, maybe we can reuse the design, or maybe we can, you know, come up with a different composition for it or something. And so that kind of helps you judge what you used to do with what you're doing now, so you can kind of compare. So, okay, back to the slide here. There are recursive relationships. Here's a recursive one, where we have an employee that manages or works for. We have a worker who's an employee. So employees who are managing other employees, essentially what we've got going on here. And then we also have relationships that can have descriptive attributes associated with them. We don't normally see this in the database class because it's kind of, when we create a database out of this, we pull, in the relationship, we pull attributes from client and book. The focus of this is slightly different though, because we're looking at more of a system, and we have a piece of data that's out here, you know, for the date of the order that was placed. We could have time, could have any other piece of information that might be associated with it that we want to track. So it's okay to put attributes on relationships when you're modeling the system itself. So for those of you who said, wait a minute, you've got an attribute next to a relationship. For database kind of focus, you don't want to do that, but system development, you can, no problem. So now we have different degrees. Here's our degree example. The degree refers to the number of participating entities in the relationship. Here we have 3. We have project, contractor, and contract that are all participating. And here's an example of 2 that are like a contract. Well, you could have a physically printed out contract. Does the project have a printout? Not really, it's a concept. But the contractor is a human being, hopefully, or a very sophisticated artificial intelligence computer or something. And so we have a combination of objects of different types that are all participating in the relationship hires. And in terms of the way that you map this out for a system, you want to include the degrees of the relationship and the participating entities all in the same. You could take and create 2 different diagrams out of that in a database world, and that actually helps you because it helps you break down the data. But you'll lose the connection of how the logical system is working. So when you're doing this for system development or for software engineering, not databases, you want to make it more complex. Actually, you want to put them all together, show the multiple degrees of relationship, because then you can see how the information is flowing between the different entities, and the participation that involves helps you create a more sound design, because what you're trying to do is you're going to build the design of the system off of this. And what you don't want is afterthoughts. Oh, so the project hires contractors, and let's say you leave this out and you have another diagram that says project uses a contract. You know, there's a project and a contract that's associated, has a contract, and you've separated them all out to simplify things for you. When you start building the system, then it becomes an afterthought, because you say the project hires a contractor. Oh yeah, what about this contract? Oh, let's put that in. But it wasn't really part of the design, you know, or the structure of the way you've got your model set up in terms of what your objects are doing and who the objects are participating with. And then what ends up happening is you end up with, let's add this in, let's add that in, let's add this in, and then all of a sudden you've got like a lack of consistency, maybe duplicate objects that are doing the same thing, and you've deviated from the diagram. So what you want to do is kind of have the diagram resemble the finished system, showing all of the degrees properly. So yeah, I encourage you to show multiple degrees in terms of what you're presenting for the class, for your project. This is the same as for databases. Cardinality is cardinality. You can't really have too many changes in terms of this concept. Express the number of entities to which another entity can be associated with via the relationship. If I have a bus and the bus has 32 seats on it, my cardinality says 1 bus to 32 seats. So I have 1 versus 32. I don't have an asterisk though. In databases, you can get away with an asterisk and not put a number on it because you're modeling a database. Who cares how many rows are in that table or how many employees do you have? you're looking in terms of a database structure. In a system, if I have 32 seats on a bus, I don't want to develop the application. It's kind of like, anyone ever order a flight on an airline? And you get to the airport and they've oversold the flight. There's only 100 seats on the flight, but there's 200 seats sold. It's like, how does that happen? Because, well, they do it on purpose, but it could have been that the application didn't know how many available seats there were. So if you build an application, then you run into problems. So if I'm building a scheduling program for school kids to take a bus, and there's only 32 seats, then I'm going to build the cardinality and specify 32. If I want to be generic and there's an unlimited number of seats on that bus, maybe it's one of those, virtual buses or something. I don't know. I could just say many. So we get a little bit more, point being, we get more specific when we're looking at the logical structure of the system versus the database approach. So here we have a one-to-one, one-to-many, many-to-many, and the way you diagram it out, it doesn't really matter. It's the tool set that you're using. Traditionally, the arrows are showing many, and the solids are showing one. And you're supposed to be able to read it either left to right to left, and they're supposed to mean the same thing. So one to many, we have one to many, many to one. This is really the same thing as one to many, or many to one. There's the opposite, many to one to many. So. And don't necessarily get concerned in terms of the symbols on the diagrams or the symbol sets you use. Just the same as the database class, you can use anything you want. If you have access to Microsoft DreamSpark, you guys heard of that? I'm still working on. In fact, that's a good reminder. I should probably write it down so I remember. You get university discounts to free software. You can get Visual Studio, actually, and you can get development tools, and you can also get Visio, which is the graphing tool that you're going to use, hopefully. It's a huge sucker. It takes a lot. You have to install .NET on your system, and it only works on Microsoft. But there are other free tools out there, or you can use PowerPoint, or you can use Microsoft Paint or something, or any type of graphic program. SmartDraw is what I used to like. But SmartDraw got SmartDraw. It's they used to have a 30-day, now it's like 7 days. Now I think it's like 3 days or something. Some student told me like the current version, it's even smaller now. Pretty soon it's going to be like 12 hours, 1 hour, 2 hours. Like, I can't really use it that long. But if you get a tool like that and it puts a watermark on the bottom of it, don't worry about it. It's not like a professional class. I mean, this is a class assignment. It's not like you have to have it without a watermark on it. You can have a watermark on it, which is what SmartDraw is going to do for you. Otherwise, I'm actually going to remember this. Actually, my TA, can you send me an email message that says, look up to see how ITU can get associated with Microsoft DreamSpark. Other universities are associated with it. You just say where you're from, and they authenticate you because there's an agreement with the university, and then you can download a bunch of free software. But I can't imagine why we would not qualify. So send me an email message. So now he's responsible. So now I can't forget, because I know it was like 2 weeks ago I mentioned this in one of my other classes, probably the C++ class, and I totally forgot until like 2 seconds ago. So, all right, back to the lecture. Some cardinality examples, so maybe if I remember okay, one last thing about DreamSpark. Maybe if I remember, I'll have it next week for you. All right, so, and I'll put something on the website or something, or actually, ITU could hopefully send something out to all students to inform them of it, if that's the case, if it becomes possible. But I'm not quite sure how long the application process goes through. So, all right, cardinality examples. A person has only one ID book, and an ID book belongs to only one person. Okay, so only one to one. And we have a person can own many cars, possibly zero, but a car only has one owner. So actually I misled you in the last slide when I was telling you about the arrows, and I just realized that I had done that. The arrow is generally the one, the nothing is generally the many. It's the exact opposite of what I just previously said in the last slide. Because what normally happens is there's a number down here that says a person can own 12 cars. A person can own 5 cars. Like one bus has 32 seats. So it's usually the one side has an arrow, and then the other side has a number or something associated with it. Or it could be empty. In this case, it's empty. Sometimes you might see it with multiple slashes next to the arrow, or on the arrow, lines going through here. Sometimes you see the crow's feet, meaning there's not just one, it's like many kind of, the crow's feet are like, they come out like this in here. And can kind of see that there's a lot of stuff going on over there, not just one. So it's a little deceiving when the way it's written on the slide, I think. But however you do it, you can come up with a legend if you want in your diagram and say this arrow, single arrow means one, nothing means many if you want. So you can come up with your own symbols. There's actually kind of an interesting one that puts a 0 here. That means 0 or any number. They actually put a 0 on the line. So sometimes you see that. So a person that can have many houses and a house can have many owners. So now we have the many to many here. So on the bottom. Design issues. Alright, so believe it or not, and then people are going, oh, I thought we were going to have a lot more than that. No, no. I'm not going to bore you with entity relationship diagram. For purposes of system diagramming and logical structures, that's all you need to know. We're not building databases out of this, so you don't need to know anything else, and you don't even have to be that specific. Here's where the problems come into place, though. We have to design issues in terms of what's an entity and what's an attribute. So it's common to actually mix them up. As an example here, should location be an entity or an attribute? Location of a project, location of a company site. Maybe we're talking about Starbucks. And we have multiple locations for the Starbucks. And we have an entity called Starbucks. Maybe we're building a software application that works at the Wi-Fi hotspots at Starbucks or something. And are we going to put location as an attribute for the Starbucks, or should we have each one of the Starbucks as different locations? Which, in terms of the database design, we probably would make location. That's kind of a clear-cut decision. But in terms of the systems design, we could put, Fremont Starbucks, Sunnyvale Starbucks. We could have different Starbucks locations, and that would actually be okay if we were showing things that were happening at the different locations. Maybe some of the locations have the Wi-Fi access and some don't. Maybe some of them are managed differently. Maybe one guy owns 3 of these or something. Actually, that's a chain. They're all owned by the same people. But anyway, long story short, can a project be in more than one location? If it can, maybe you want to put it out there and can a Starbucks be, depends on how you want to represent it. We also have the same situation that goes on in terms of the relationship. Is it an entity or is it a relationship? In terms of the complications, generally relationships for actions between. So we're looking at the relationship is supposed to be one person has an action with another person. An entity has an action with another entity. So whatever makes sense in the application context is what you use. So don't get stuck in database speak and think, is it a multi-level attribute? Is it a single attribute? We're not worrying about any of that stuff. Instead, what we're worrying about is looking at to see how the system should be designed. Because we're looking at connectivity between, if we're talking about Starbucks and Wi-Fi access, Starbucks aren't going to be talking to each other. They're probably going to be in separate islands of their own, maybe. Well, who knows? Maybe we can change all the Starbucks together. So, let's take a look at the symbols. We have the one-to-one, many-to-one, the many-to-many. We looked at a few minutes ago. And we looked at these throughout the examples just to clarify the entity is always a rectangle. The attribute can be a bubble. It can be written inside of the entity. Different tool sets are going to give you different symbol sets, but they're going to be relatively similar to this. And the relationship is always similar to a diamond in shape, normally. And here's an example of an entity relationship diagram. This is more along the lines of the level that you'll be putting together for your project, where we have, again, the same concept where we have a project that employs employees, and the project eliminates aliens. It's Ghostbusters. So you guys heard of Ghostbusters? No? Too old of a movie. It's interesting when I talk to international students what they've actually heard of and what they haven't. If you talk to any U.S. person who's been around for a while, Ghostbusters, because we got sick of it. We had Ghostbusters 1, 2, 3. It's kind of like if I said The Hangover right now, movie. Well, 1 and 2 were practically the same movie. So but you go, oh yeah, 1, 2, 3, 4. But if we only had 1, probably wouldn't have remembered it. I don't know. Who knows? Anyway, different topic. So here's an example. Any questions in terms of what you need to do for your projects? I say just 1, but as I mentioned before, you could have 2 or 3 if you wanted to. You can have as many diagrams as you want. The more, the merrier. So how do you start out doing this? You identify the entity sets. So in terms of the design philosophy, you sit down, you've got your list of requirements. And then you say, well, what are my entities in this thing? So let's say I'm building a university registration system. I have students, I have teachers, I have classes, I have rooms the classes are in, I have the number of units, I have all these different pieces of data. Some of them are data or attributes, some of them are entities, some of them are relationships. If you just make a big old list, then you can kind of put them into categories. You can make a sub-list out of the list, circle and X out, and kind of troubleshoot the list a little bit. Describe the entities with attributes. So say, let's say we have classes in our university registration system. Well, the room number might be associated with the class. The teacher might be associated with the class. The students who are registering might be associated with a particular class. And then we can kind of set those attributes in terms of what information do we need to store about a class. And then look at the cardinality of the relationships. Well, do we have a maximum count? Is there a wait list for this class? Is there multiple sections of this class when one section fills up? Or is it an unlimited number for the class? And that's how we kind of get the starting point for putting it all together in terms of creating the diagram. In terms of a simple modeling example, let me take you through one that's a system-oriented, not a database, but a system-oriented example. So every department within the company is in only one division. Each division has more than one department in it. And there's no upper limit on the number of departments that a division can have. And we're building a network system, let's say, to organize the information that flows across or something, or an application that's going to be working across this particular environment. So number one, we define the entities that exist here. So every department within the company is in only one division. Each division has more than one department in it. So we have divisions, departments, and employees. We really haven't kind of showed anything about it. And this is an interesting example because it kind of flows in a different direction than what we normally have seen so far. So you can kind of see the entities as a department, a division, and then employees. And then we define the relationships. We can say, well, a division contains departments, and the departments manage employees. And so we can draw lines between them. We're not concerned about, cardinality, or at this point, we're not concerned about, the relationship degrees or anything. We're just trying to essentially put it out on paper. And then we would take a look at and define the cardinality and say, well, at this point, division, and here's our multiple arrows here. A division only has one department, many departments in one division, or many divisions have many departments. Or we can essentially map out the cardinality using any type of symbol set that we want. And we can actually do this for our project. We didn't use a diamond symbol because we don't have multiple participating relationships. It's a very kind of simple example in which we only have 3 entities, and all 3 of them work with each other. And it kind of worked with it in sort of this cascading approach. So in a lot of systems diagrams, we kind of see it sometimes cascaded, which is a little different from the database people. When you see it usually going left to right, right to left, top to down, we kind of made different kind of looking diagrams. Here you can actually kind of make it hierarchical, cascaded, or you can you can be more creative with it, because we're not trying to turn it into a database. We're trying to turn it into a system. And we're not concerned with the same information or the level of information. So, not to say that it's a sloppier approach, but it is. It's a higher level, sloppy approach to what you would normally do if you were interested in drawing a database out of it. Because here's what happens in the real world. You take this analysis, it turns into a design document. Somebody in the process of the design, a data architect, takes a look at this and goes, oh, let me create a database-oriented entity relationship diagram. They create their own diagram out of it. And they kind of take this as a starting point, and then they focus on the database components of it. So it's this is a higher level abstraction of the one that you would actually create to actually implement the database if you were taking that approach. That's one thinking. Other people try to go all the way with the database and say, well, this is going to lead to our database. Which is kind of interesting because you'd think that the data flow diagram, the next lecture I'm going to give you, would give us our data, but it doesn't. It gives us our processing. So this actually gives us our data, which is kind of interesting. All right, here's our standard notation. Here's the other examples I kind of talked about. And with the line coming through, say 1, 1, or you can see a 0, 0 or 1. This is going to be the same. The relationship is always going to be a line. And here's our crow's feet example, to say 1 to n for any number. We usually see the n's in systems instead of the manys, because we're not looking at many multiples, we're looking at n's or any number. And the number might also be substituted with a real number. So here's our diagram with our standard notation attached to it. We just added some crow's feet to it here. We put a line through it here. So this is as simple as your diagrams can be for your systems. They don't have to be complex. And some more notations here. We have a course has enrolled many students. One course has enrolled one or more students. One course is enrolled in one student is enrolled in one course. It would be a one-to-one. Or a loan. One loan refers to one book. One book is referred to as one loan. Loan to book, book to loan, one-to-one. Just more examples if you haven't seen enough. The many-to-many, where we have one supplier might supply more than one kind of part, and any one kind of part might be bought by any number of suppliers or different suppliers. So we have the crow's feet on both sides to go. Many-to-many. Doesn't require very much artistic skills, and doesn't require diamond symbols. You can just put the word of the relationship on the line. What you don't want to do, and this is the caveat that always people run into, you don't want to give me sentences here. Don't put the sentences out here. Don't put a verbal description or a written description of what it is you're telling me. That's why you're creating a diagram. The diagram says 1,000 words. We don't want to read it. We just want to look at the diagram. So don't add too much text to your diagram. I guess what I'm saying. And here's some more examples. And this is actually kind of showing you different types of relationships. In this particular case, where we have a customer that is associated with property. And we have a customer that can place an order. We have teachers that teach students. So we have different types of those relationships that are all represented the same way. Simple hospital system. We have a ward, a nurse, a doctor, a patient. Patients suffer from many ailments. Many patients suffer from many ailments. Kind of realistic, I guess. Many different nurses care for many different patients. Many different doctors treat many different patients. One ward has patients in it. Usually you belong to a ward, unless they move you around every 5 minutes and you're in different wards. So that would be a simple hospital. So here's a college system. This is the level of detail that you need to do. This is your entire system. This is an entire hospital system. This is an entire college system, where we have a department that has lecturers in it, and we have courses, and the students take the courses. It's only showing a particular part of the college system. It's not really showing you the registration or the add drops or anything. So what normally ends up happening is you have one diagram here that says college system, and you have another one that says add drop system, and then we have the tuition system. Something of that nature. Alright, so think about your system's attributes and your entities. That comes directly from the requirements. If it's not in the requirements, it doesn't end up in the diagram. So we're not done yet. That was the first half of today. So now we have the flip side. You did not get this in the data flow. And coming from the description, you did not get this in the database class, and coming from the description, you'd think you would. It's interesting. The data flow model is showing you the processing. and how the data is translated from one process to another. And this deals with process bubbles in terms of what it is we're showing. So it's based on the notation that systems can be modeled as a set of interacting functions. The data flow diagram does not translate into UML. Why? Because UML shows both processing and data together. This is only showing you processing. It's leaving out, believe it or not, even though it's called a data flow diagram, it's leaving out the concept of the data entirely, which is why the entity relationship and the data flow diagram are usually done together. So if you see someone using an entity relationship diagram, they're going to have a complementary data flow diagram that goes along with it. You need both, because you're showing one is showing the processes, the other one, the entity relationship, is showing you the data. Turns into the database in terms of the system model. So let's talk about data flow for a few minutes. If we were creating a UML equivalent diagram, which this does not translate to, we would be looking at sequence diagrams. We would be looking at state machine diagrams, or anything having to do with processing. Hierarchical diagrams can loosely translate, but we can't take the diagram and turn it into a model. We can't turn it into a UML, anything. So what we're looking at here is looking at the data flows. So graphically representing the external entities, still looking at entities, processes, the data flow, and the data sources. So usually you start out with the entity relationship diagram. You've identified your entities, your relationships, your attributes, and you have that all laid out. And then you take those entities and you look at the data flow. You create the data flow diagram. You could create it from the entity relationship, but it's really a bad starting point, because the focus of the entity relationship is to show the associations between the entities, and it's not really showing you anything about the data. So you kind of have to actually start from scratch in order to get the big picture, in order to put it all in correctly. So graphical picture showing you all of the main requirements of the information system in terms of its inputs, processing, and output, and the data storage. What's going to come out of it is going to be your storage. It doesn't really specify, though, how or what type of storage is going to be resulted from that. So now we're looking at kind of a different symbol set, but there are some similarities. We have, and I'll relate this back, this is only talking about data flow diagramming, this particular lecture, which is number 6, I believe. The last one was number 5 if you're downloading the PowerPoints. We have arrows. We don't have cardinality. We don't have to worry about that. But we have directional arrows, and the directional arrows usually have an arrowhead on them showing the direction of something is coming from point A to point B, and it's in the direction of point B, which is the destination from the origination point. We have this most important symbol on the entire diagram is going to be the process bubble. Usually the process bubbles are labeled. There's usually a number. And you have a number because you end up with process descriptions that come out of it. And you'll have to create those for your analysis document. So you're going to start out the format, you're going to go to an entity relationship. So the next section you're going to do a data flow. Next section under that you're going to have process descriptions. So number 1, number 2, number 3. Those are coming from your data flow diagram. Then you have this thing called a data store and a terminator. Doesn't the terminator look like an entity? It is. One type of terminator is the entity. Not all terminators are entities, which is why they're not called entities, and they're called terminators instead. And I'll talk about that in a few minutes when we come look at an example. And you see that in the diagram, and it'll make more sense to you. The data store is interesting. It's kind of an open-ended terminator. It's being stored as a component of the data, but not the complete data, which is why there's an opening essentially on the box. It's not a complete box, it's a partial box. Sometimes you see the symbol with an underline, or you don't see actually the whole thing here either, because it makes it easier to see it. Let's take a look at it. I think I've got a picture here. Here's a picture. And the data store looks like this in this particular picture. In the previous slide, it looked like this, the data store. So sometimes when you see it, it's more common to see it this way. Because why shut off one? It's too easy to say, oh, that's a typo. This is clear that you intentionally left the sides open. You left it open because it's a store. It's not permanent. It's not a database. A terminator would be a database going into something, and the database would be an entity, well, it's actually not really an entity, but it would be a terminator. But this diagram's not showing you a terminator yet. Instead, we're looking at the processes, which are always bubbles. And so we have a customer request that goes in, and we've left out the numbers on the boxes here. But we have this, receipt. We receive the request from the customer. Let's say this is a shopping cart application. So the customer request comes in, and we've sent the customer an invoice to say, hey, thank you for your order. Go to PayPal and pay for your order. Or, let's process it and let's use your balance or something. So the customer goes to PayPal, and this would be, let's say, a PayPal process that said, process my order through PayPal. And then we have a receipt that comes out. And then over here it says, well, let's ship the thing. So this would be like a shipping bubble or something. So all the functionality is in terms of the bubbles and the processing, and the arrows are telling you, well, we could go for PayPal, or if this customer has a credit already, we could just go to the shipping. Or if we're in PayPal and PayPal rejected it, we could come out here, and this could lead to something else, like maybe a credit card. Give me your credit card if you don't have a PayPal account or something. And then here it could be, well, here's your data store. And PayPal is actually kind of a good example. We have a transaction that occurred. The seller is going to get some money. The buyer is going to be lost. It's going to have something deducted. So we have a credit and a debit going on. Those are going to be in terms of multiple data stores. We show it as one, meaning we have some data that's coming out of this that's going to be stored somewhere. But we don't have a database. We just have these. We have multiple pieces, but we're not showing cardinality. Instead, we're showing the result of whatever happened in here. And this could be multiple pieces of data. It's just data. Which is kind of different in philosophy than the entity relationship, where we're thinking one bus has 32 seats in it. Because it's the logical structure of the system. Here, we know we have something coming out of it. We might want to keep track of it. We don't know yet. We don't know what we're going to do with it yet. We haven't decided. We haven't made any decisions on any of these diagrams. We're just explaining the system in a lot of different perspectives so we can understand it clearer. Here we don't have anything coming out of this shipping. Of course, this might be, product shipped. We might have something else going up, wrong address or something, or we might have some error codes or something coming out of that. But what we're looking at is the flow of events from point A to point B with arrows showing the directional flow. And sometimes it stops and sometimes it does. And here we have a terminator. If we think about an information system, the three components of an information system: input, processing, and output. So we got input that's coming in. We have what's called transformation that occurs in the bubble in terms of the processing. We have output that comes out. Output could be a terminator, purchase order, receipt. Think about all those entities that were concepts: invoice, project, customer, customer name, customer information. Usually it's, a sales receipt actually is kind of a good example. We have multiple inputs that come in, but we're only saying that the information is coming in. This information, which differs from an entity relationship, because an entity relationship we're looking at, well, what information is coming in? Person's name, the credit card number, the number of items that they want of each one of them, the cost of each one of the items, if we're talking about a sales receipt, the tax, all this information, what state are they in, are they getting it shipped, are they picking it up at the store, when do we need to charge them, do they have a discount with us, all this information is just the input. And the transformation is all a calculation. So we take the number of items by the price of each one of the items, we add it together, we add the whole thing together, we charge some sales tax, we tack on a shipping charge, and we subtract 15% because it's a returning customer or something, they have a discount code in there. And then the output is, here's your sales receipt. And in between, we now have a directional arrow coming in. If you notice, We've switched the data store. Instead of storing the data, now we have a data dictionary. And the data dictionary might be, in this particular example, the customer lives in the state of California, in Santa Clara County, and the current tax rate is 9 something, isn't it? So it's like, what is the current tax rate? For the, in fact, it's different depending upon which city you're in the same particular county. Some counties are cheaper than others. So the data dictionary is where this piece of information is coming from. It's going to be the local tax rate. Also could be maybe, is it FedEx or is it UPS? Or is it US Mail? And what is the shipping charge? All the stuff, the information coming in from a known source or the data dictionary could be referred to as a repository. It's generally called a dictionary. And we don't know where the information is coming from. It might be in a database, might be in a file, might be coming from multiple different sources. And it's all coming into the transformation bubble. So you can kind of see where the data flow diagram is kind of a high-level perspective of the processing. And we're primarily concerned with the transformation or the processing that's occurring. Our terminator is an external entity with which the program system communicates. So by definition, here's your formal definition. I've kind of explained it already, I think. Typically, it's a person or a group of people, an outside organization, a government agency. It could be, in this particular example that I gave you, which was different, a concept, such as a sales receipt. It doesn't have to be a person, place, or, well, person or place. It could be a thing. Person, place, or thing. Here's some examples of entities, or terminators, I should say. I don't want to call them entities, they're terminators. And we have a university information system that's making records available. And so the records are available to the Ministry of Education, and then maybe it comes back here, so these guys talk. And the parents of the students, available student records are given to the parents, and then the request for study records comes in from the parents to the university information system. So you can kind of see we actually have to draw the directional. I like this diagram because it's showing you the terminals, it's showing you the processing. And it's showing you 2 arrows instead of 1, both showing the same thing. So just don't think about the relationship and just think about how is the information flowing. The data is flowing this way. The records are going to the parents. And the parents are making a request. So the parents have to send some piece of data to this university information system. A login. Maybe they have to fill out a form or something. They have to do something to input something into the university system to get some output. So we're looking at input and we're looking at output going from the same terminator to the same process bubble. Here's a library system. And this is where people go, wait a minute, what happened here? Now we have 3 inputs and outputs combined together between the process bubbles. This is very typical. So we have a library user, an entity terminator. We have a library assistant entity terminator. This is pretty good. You know, the return date, the library assistant is going to say issue a library item. Well, first thing you do is the librarian says, well, this book's going to be due back in 2 weeks. 2 weeks from now is going to be such and such date. So the library assistant is giving the return date to the library item. And this process is the issue of the library item. It's the I want to borrow the book. It's a process, not an entity. It could be a receipt that you get out of this. We don't know yet. What are we going to get? We're going to get something. We're going to issue an item. It's going to come out. This output is going this way from the process to the library user to say, here's your item. What do you get when you actually, in the old days they used to stamp the book with the date. You brought the book back to check the date, and like, oh, okay, you're good. Actually, in the old days they never charged you, when it was like 2 months, 3 months. People used to bring books back that were a couple years old. Here's your book, we found it. But I don't even, do they even loan books out anymore? Times have changed. Now you just download the PDF. Alright, so the library user requests an item, and they also have a library card. So the library card, the item requested, comes into the issue library item process bubble, and in return they get the issued item that comes back out. This is very typical of your average day data flow diagram. This is what they look like. They're not very much more complicated than that. Because when you think about it, this is the entire process of borrowing a book from the library. So we would have different processes with different process bubbles for different activities that might occur in the same system. And here they are. So we have a little bit more complicated, but this is the library system, the complete library system. That was just one part of it. Although the label on the top is kind of deceiving, this is just an item, one of the bubbles. In here we've got that bubble. Here it is here. Item, issue item. We still have the library assistant who is bringing in from the return date, providing that. But now we've got this output that's going to the library user. We still have that going on. This is the same as what we looked at, but we added some more sub-processing. As an example, we still have the other two. These are from the other diagram. We have the library card that's coming in, and we have the requested item that's coming in. But it's coming into two separate process bubbles. So if we have a library card, we're going to have something that says that check the user. Has your library card expired? Are you the owner of this library card? Does the picture match? It's kind of like, is this your credit card? Do you have balance left on it? Stuff like that. If they do, the user status goes into a check item. Okay, I know you said you wanted to request this item, but we even have this item? So we have to find out if the item is even available in the library. If it is, update the user information. And then from the user database, and we can put database up here if we know it's coming from a user database. It doesn't have to be a data repository. It doesn't have to be a data dictionary. It's a database. So from the database, because it would be incredibly bad not to have a database for a library system. User details from the database are going to the check the user, and user details are going into the update user details. And then we have both directional arrows coming to and from the database to update the details. And then we have from the check item, we have the user ID that's coming up here from the item issue. We have the item ID coming up here. So we can update the user details to say, on this particular date, and here's the return date, user XYZ requested to borrow this book, user database design, and it's due back on this particular date. So when you go to return the book, it's just like video rental. They say, hey, you had it out a day longer than you're supposed to have it out. Or, yes, we got the book back. This user is now able to borrow more books in the future or something. Pull your card from you. And then down here we have an update details that go into an item database, let's say. Because we might have two different ones. We might have a user database that's giving us a list of library users. We might have an item database giving us the current inventory of the library system. That's actually the complete library system if you think about it, because it's doing the processing for both the checking the user, checking the item, and also issuing the book, or issuing the item from the book. So that is probably what you're going to do, something along that lines. You only need one. You want to put the whole system in there, though. Interesting. This is called user database, not user table. The terminology just says it's a database. These could actually be the same database DBMS application, and these could be two separate tables. But it's a data store because we're looking at the symbol that we're using, and it's a data store. But we're saying it's a database-related data store. We don't have to actually put that there. We could put data dictionary there if we didn't know. So it's not like a hard said fast, this is how you need to implement it. It has to be a separate user database and a separate item database. That's not what the purpose of the diagram. It's making a suggestion that is coming from a database. That should be stored in a database. Questions at this point? Yeah? No. In one of the previous examples, we didn't. We had a data store that was a data dictionary. The data dictionary could be temporary memory. It says when the user logs in, it sets some parameters from the environment variables to say, hey, this user's in California, and they're in Sunnyvale, and the current tax rate is such and such percentage. So there's a dictionary Think of it more like a repository if you want, or a little dictionary, where you can look up some terms. It could be environment variables, they could be log files, how long has the user been logged in, all sorts of different information can come from that. Does not guarantee that you're talking about a database. Actually, that's a very good question. Anything else before we step forward? Oh, I'm not going to step forward too far. So the concept being, this is a box. You can't see it. It's very faint. Actually, there's two boxes. These are. You actually can sort of see it better, I think, on the transparency. You can see it better on the screen, I think, than I can see it on my computer. But these are round boxes. Round boxes. Excuse me. Circles. Round circles. So, for process bubbles, same examples we had before. I guess I should darken those. What we're looking at is a math problem. This is kind of showing you or demonstrating the point of how you're supposed to put this together. So the data flow diagram that is evaluating arithmetic expression A plus B times C plus D plus F. So we can actually show the order of precedence, we can show the calculations and the processing, and we can show the output, essentially. And so we have A and B that are going into an add one process. And here we've put labels on them. We could put labels on them. We could put numbers on them. We've identified them. So A and B going into the add process. And we're going to also say C and D, and this is order of precedence is determined by these simple math, by the brackets. So C and D are going into add 2 down here. And we have the sum that's coming out, sum 1 and sum 2, that are being multiplied together. And then going left to right in order, we can say this product is going to be added with F. So we have F, and the product going into add 3, and then we have our result that's coming out of it. That's what you're doing for your system. If you do this correctly, your math will be correct, hopefully, and your system will produce the correct results, hopefully. So you don't put an ATM card in a machine, and then it asks you for your password, or I don't know, it doesn't know. Usually it's supposed to be a PIN, let's say. It doesn't bring you to the main menu and then at the end ask you for the password or something. So this helps you kind of organize the prompts, helps you organize the user interface, helps you organize the use cases. So you could take a data flow diagram as an example and translate it. I shouldn't say translate because nothing translates well out of a data flow. You can use it as a foundation to understand the system to create a use case scenario, or use it to do a sequence diagram. And when I said in the beginning, you can create a sequence diagram out of it. What is this? This is a sequence that's going from point A to point B to give you a result, following some sort of rules of math. In this particular case, this can translate with a lot of work to a sequence diagram. But in the same process, what you're doing here is you're understanding the rules, and you know how the process is working, so you can put together. You have to start fresh with it. It doesn't translate quite well, but gives you a starting point to actually work with a UML sequence diagram. So our data flows are usually used together with processes, just to reiterate the point. So they're used to connect processes. So oftentimes you see processes connected to other processes, which is what we saw here. You never see relationships connected to other relationships in a relationship diagram. Entity relationships, you never see relationships. You always see one entity, one relationship, and another entity in that sequence. Exact opposite for data flow diagram. Instead, you see processes connected to processes connected to processes, with a couple of little terminals on the end, terminatings, or maybe some data stores in there too. So you have indicating that the data items are moving from one process to another. And here's our example where we have study records. You earned a grade for something, for a class. And we have something that says, well, let's divide the records out. And we're going to split this into two groups. Students who pass and students who fail, or qualified students and then failed students. And then we're going to take all the qualified people and we're going to sort the records out. And then we're going to send them all an email message. Say, hey, you qualified to graduate, and you're all ready to go. And then the other group of people, you're going to give them your failed students. You're going to go out and say, give recommendations. And you're going to say, hey, you know what? Maybe you should retake this class. or you're not quite ready to graduate yet, you have this and this and this to take or something. So you can kind of see how this process leads to something happening over here with this process leads to that process. And you're sort of filtering it out in a sequence. You're starting with a big group of records, and you've divided it out into two smaller groups. So a lot of times what you're doing is you're dissecting your data in some perspectives. You're taking a big piece of data and you're breaking it out into little pieces of data, categorizing the data, organizing the data, processing the data. Sometimes, if you've seen in the previous example actually, the data comes in, where did A and B come from? Or C and D? We have no idea, it's not our concern. So we don't have anything out here, it's empty. Where did these study records come from? I don't know. They just came from somewhere. So this is another thing that we have different in a data flow than an entity relationship. If you have this in an entity relationship, you'd be like, what entity has the relationship with this? It's clear. Here, it's vague. We just have student records. It may not have come from anywhere. So oftentimes students don't like to have arrows that just come from nowhere. They think there's something wrong with it. It's like, not really. We don't know exactly where the student records came from. We could have another diagram that showed where the student records came from if we wanted to, if there was some concern with it. Where do those student records come from? So important points about data flow diagrams. The data flow should carry one type of information. So don't name a data flow as student and professor and administrator. So one type of information per data flow. So let's go back and take a look at the data flow. Here's the data flow. We have qualified student records. We have failed student records. We're labeling the data flow just the same way as we kind of labeled them here. You don't use diamond symbols. You put library card. Requested item. You don't want to put library cards, plural cards, or anything too generic. You want to be very specific in terms of the way that you're labeling it. Otherwise, it makes the diagram unreadable. So the readability of the diagram is in the nature of how you're being specific in terms of the data flow. So student, professor, administrator. Well, what about the student? How about student ID, or student name, or student address as a piece of data? Student. Because some people will say student information. And this is actually kind of vague. Well, not really. I guess not. Requested item. We're assuming we're talking about a book. We could have made that a little clearer and said book, requested book. Maybe, you know what, maybe it's not a book. Maybe the library system. Yeah, actually library systems these days have DVDs, CDs, books, all sorts of different things. So library card is specific. Item issue specific. User ID. Item. I guess those are good examples, I guess. The data flow can carry a composite data item. So for example, university member, which may consist of three components: a student, a teacher, and an administrator. So don't worry about your data flows containing multiple items. They can. You can have student records. Qualified student records is probably the name, the number of classes they've taken, the GPAs they've taken in the classes, when they took them, who they took them with, all sorts of different information. So we've got multiple different pieces that go together. And the data flows show directions. So you can kind of see the flow. And here's our flow directions. So we have student records. And the student records come in, and this is something new I haven't shown you yet. We have an arrow that branches out into three separate arrows. This isn't cardinality. This isn't the crow's feet. This is three different processes. So some of the students' records, the same student records, I should say. This is the same student records. Goes to faculty offices, goes to university students, student office, and goes to professor. If they were different, we would put labels on here and say, well, the faculty office is going to get the grades from the student records. And these guys are going to get, I don't know, surveys. These guys, I don't know what they're going to get. Nothing usually. So little pieces of subcomponents of the data if we were branching out. But this is basically telling us we've got the same thing going all three directions, which what we can do. There's no problem with that at all, and it's not cardinality. We also have this thing called converging data flows. So now can we branch them out into multiple directions? We can converge them together, the exact opposite. We can say that, because we can store multiple data in here, we can say that we can provide student data from the student, and we can divide out professor data from the professor. And then we can also provide administrative data from the administrator, send all this stuff together, converge it all together, and send it to the classified data process. And then out from here we have the classified data that comes out of it. This process, classified data, is going to put it all together and organize it for us. This could be like a scholarship application. So we have the request from the student, the form, the letters of recommendation from the professors, the transcripts or the things from the administrator to show how you've been doing. All this puts together, and we have classified data as the scholarship application that might come out of that. And then we can process that further and say accept or reject or something of that nature. So that's our converging data. And then now we have an interesting thing to kind of think about, because most people who like entity relationship diagrams like it because it's clear. As I've been mentioning so far in my comparison, it's very explicit. It's only showing one relationship, and each one is drawn out. Here's where data flow kind of messes things up. Data flows do not answer any procedural questions. We don't know. Here's the process bubble we have in the middle. We have A and B coming into the process. Out of the process, we have C, D, and E. Oh. We don't know if A is part of C, is A part of B, or D, E. Is A and B part of C? Is C and part of D, E? We can't answer that question, and we shouldn't try to answer that question, because we don't know about the relationship, and we don't know the procedure. We don't know exactly which piece of information is leading to which other piece of information. This helps us, if you can kind of think about this way, we know maybe this is financial aid request, and this is the number of classes you're taking and what your financial need is, and this is what your application is. And then out here might be different financial aid companies who are providing loans. Or maybe these two are loans and this one's a scholarship. Or maybe, and these are all of the different options that might be coming out. And this is where we're sending all this data to from the process. And we may not be sending all the same pieces of data either. And we can't answer the question. So when you look at your diagram, you're going to be, I can't answer that question. It looks wrong for some reason. To people who like entity relationship diagramming, this looks wrong. But it's right. Because it's a data flow diagram. And you know the data comes in and the processing occurs, but what comes out of it? We don't really care what comes out of it. And the reason why we do process bubbles, then we explain what comes out of it. So at the end of the data flow diagram, you'll always see data flow diagram followed by process descriptions, which is why people put numbers in here. They go, number one. This is added to this and it's divided by that, and now we have the GPA. GPA goes off to C, to the registrar's office. And then we have, this is how much these are how many courses they took, and this is how much it costs per unit, and this is how much they owe us. So this goes off to the registrar's office, or the, what do they call it? You pay. I don't know, the office that collects the payment. And then this one here, E, is like we've decided, we're going to check to see how you're doing, and we think you're on academic probation now. So this E is going to go off to another direction. And in your process bubble description, you're going to be explaining all that stuff. You're going to be saying, here's the flow, here's how it's going to work. And you're going to use, and I have a couple of examples in the lecture notes that accompany, that's like the 160 pages of SE notes. You can use structured English, you can use words. It's probably easier to write it out in English, use words for it. You could write pseudocode for it, you can write an algorithm, you can document it like an algorithm. Because what if this is an algorithm? A and B come in, and then we get a credit score that comes out based on 3 different indexes. You could show the algorithm. So how you document the process bubble is dependent upon what's actually happening in the process. So it could be something where you haven't really decided how you're going to implement it. And in terms of your description, it might be, well, A and B have to be combined together. And the result turns into this and that. Now, you can be very vague as well. So it depends on the level of detail. And most people start wondering, well, what does it matter then? Well, the more detail you provide in terms of the description of what it is you want, in terms of the how for the design document, the better or the closer you're going to get what you want. The more specific you are, it's actually counterintuitive, the more specific you are in determining if you're writing the algorithm, you're giving the pseudocode, you're saying this is the algorithm, the less likely it is going to be that you actually get what you want. Because there might be a problem with it. What if you made a mistake in your pseudocode? What if the algorithm is not the best appropriate algorithm? Instead of using I don't know, a binary search, it's using a, I don't know, some non-efficient one, and all this was in alphabetical order, you probably could have applied a binary search to it or something, right? You could have done something that was more efficient, but the implementer is going to take this and follow your instructions. So just as long as you say, hey, you know what, these need to be combined together, the implementer can combine it in any fashion that they want to combine it in. So which is kind of counterintuitive, you think. Because the more specific you are, the more you're going to get what you want, the more you're going to get it implemented correctly. The more vague you are, build me a house. Okay, you're going to get a house. You're guaranteed to get a house. Give me 3 stories, 2 bathrooms, 5 bedrooms, some extravagant house. And you spec it down to the point where it's like, well, we can't find the flooring. We can't build the house. Your flooring is out of stock. Then all of a sudden your kitchen doesn't get finished because the flooring is out of stock. And they can't, because you didn't give them any other choice. They couldn't substitute it with something else. Happens. With a house, you have partial house with flooring missing until the flooring comes in. With a software package, you don't get anything. It's hard to divide it out. You can't use half of the package normally. It's all or nothing. So you want it to finish. Okay, so some concluding thoughts on data stores. These stored describes a single or a set of data items. It doesn't necessarily describe a single database or a table or a column in a table. It's very vague. It's a single or a set of data items. Data items can be any sort of data item. Example, a file, a database can be modeled as a data store. They're modeled the same way, which is why you see in this process, in the descriptions on the diagrams, it actually said database, user database, item database. You'll see that wording used a lot. Or in this other previous example, we saw data dictionary, meaning it wasn't really a database, it's a dictionary. Data dictionary is a generic term to say something other than a database. You don't have to have anything in your system that says data dictionary on it. Who puts a data dictionary in the system? Nobody does. So. But maybe it's a text file. Maybe it is a database eventually. Who knows? And the graphical representation, one of the following representations can be used in representation A, only give the names of the data store, which is what we did kind of, while B gives the names of the data store that's going to be used to reference the data store in the data flow diagram involving many different stores. So you can give both the name and the number that is used in reference. So sometimes you can actually number the data items. You can put a name on the data items. All is up to you in terms of how you want to express it. Most people would actually just commonly represent it by a name. So it gives the name of the store instead of a name and a number that's associated with it to reference it. In fact, you see in here, I mentioned before, you can number the processes as well. The processes in the data stores are numbered because then you can track the data. If you could put a name on it, a number on it, you could say, oh yes, that's the user database, or that's the user database. And then you can refer to the user database to the user database. Because what ends up happening is you get the same thing with different names or different numbers. It's like, how can we have 2 different databases? Or how can we have 2 different user databases or 3 different ones? Aren't they all the same? Then we have inconsistencies that occur just naturally. And as I showed you before, this is what we've been looking at so far in terms of the symbol sets. And in A is just the name, which is what we've been looking at. In B, we see it broken off with N for the number. And then this is one of the reasons why they close this end and they leave this end open. And in terms of the symbol, because you could put the number out here. If you're not going to put a number here, I'd leave both ends open. It makes it easier to see it. Some people, as you've seen in some of the previous examples, take the N out in the line, and it's just all name, and then there's a closing end. Either way is correct. It's just you're going to find the same problem that you do with entity relationship symbols. Every tool designer has got different sets. You pick the set you like the look and feel of. That makes it easy to look at. So most of them will give you this. 90% of them will give you this. Visio gives you this because it wants you to number them. Because if you number them, then you can put it in the data dictionary. Because the concept of the data dictionary, which I actually covered a couple weeks ago, was that you have number one, name, and then you have description. That name is equal to, name is the name of the user, and every user has a name associated with it for the library cards, or social security number. It has three components of it. The first part gives you the state in which it was issued, and the second part gives you the year. The third part gives you the sequence or something, which actually is true. Something. There's a scheme to the social security number. I don't know if that's exactly the same, but I think the first part is the state, though. Anyway, so you can actually come up with a naming convention in your data dictionary. You can have this is item number 1, item number 2, item number 3. And then what you could do is pull in why I keep calling it a repository. You could pull out of the repository in the dictionary and say, give me something about name. How about number 1? It says name on it. Okay, use name. So we don't have to keep just one. And one could be in this diagram, one could be in that diagram, one could be in that diagram over there. And we can kind of see how one's used, or name is used throughout the entire system. Store connecting. So we have connections for the stores. And here's our connection. We saw this in a couple of different examples, but to give you the concluding thoughts on the rules. Stores are connected to the processes by data flows. These are what's called the data flows. Those are the directional arrows showing you the data flow. The data flow to the store from a process means that you're writing or updating of the store, writing or updating of the store. And then the data flow from a store to a process means you're reading it from the store and you're using it inside of the process. So the student is going to talk to the teacher. She's going to say, I don't like my grade. Student comes up to the teacher, I don't like my grade for this course. Student says, all right, give me a few minutes. I'm going to go down to the student records. I'm going to look it up. Oh, I gave you an I. Oh, so I take that I and come back up. Faculty office says, this student got an I. Incomplete. It means they didn't take the final exam. The student office goes out and updates the student records and says, oh, you got an I. So go back and take the final exam so you can get a grade or something. So we get reading from, getting from, sending it to ins and outs in terms of reading from and writing to. So we don't have to say write. We don't have to say read. It's assumed. So in this particular example, it's proper not to actually put a description on here. Like get the student record, read the student record. It's kind of assumed already. It's okay though if you put read or get or listen to, find, search, because then you're more specific, but you don't have to. In fact, the better diagrams have fewer words on it because it's easier to read sometimes. But sometimes you want to be specific. Like in terms of that library card, each one of the data descriptions, the data flows, had a description next to it. Each one of those, which kind of tells you it's the library card that's going into the check user. It's the user details that are coming from the user database. But it didn't say get user details, update user detail. Well, so this does update details. I guess they could have said retrieve details, update details. So again, it's an art and a science. You can be very specific or you could be very vague. So. In terms of the contextual level, this is our first example of a contextual level diagram, and data flows actually fall into this category. So we have a source. We have a source that looks like an entity or a terminator. We have a terminator over here, another source. Not really a source, it's called a sink actually. And then we have the system. and the system is doing a process on it. This is 0 for process bubble number 0. From this source, we have database 1, database 2. So this could be project, employee, teacher, student. We have information that comes into a process bubble. Here's all your assignments. Here's all your criteria that was put into the system. The system said, okay, we got a grade. Here's your transcript. So the sink is the finished product in terms of the terminology. The source is the origination. So instead of saying origination, destination, the terminology is we have a system or a process. So it's proper to call it a system or a process, because what you're doing is you're processing the data. We have the source, we have the sink. The sink is just, it's not really, you could call it a terminator as well. So it's pretty much the same concept, but you'll see that in terms of the context. Here's a low-level data flow diagram. That was a high-level contextual showing you the entire system. Here's a low level. These are examples of the different levels of abstraction that you could apply to this concept. Same thing as a data flow, as an entity relationship diagram, where you could draw one diagram of the whole context, or you could draw one small diagram showing you just the registration process or just some other process. So here we have a data flow 1, data flow 2, going in process 2, process 1, and here I put the process bubbles in here. In the process bubbles I put the numbers of the processes. I've also labeled the data flows. You can do that as well. So here, outside of the entity relationship diagram, the data flow diagram is the one where the labeling actually counts the most. It's how you're labeling it. It makes it readable. Makes it easier to understand. So, and we have our data store down here. And we have our data store. We've got a process flow coming out. You don't have to actually label it, though, unless there's a sequence to it. Unless 1, 2, or 3 happens to happen before 4 or 5 or something. And here's another one. This one is using colors. So we have a data source. And the data, this is a source and sink and process. It's the same terminology as in the previous diagram. The data source to a process to a data store. This might be a log file. This might be something. To a process to a data sink. You can call these terminators if you want. You can call them sources and sinks. So it's just you see it in the literature used a lot, actually. Here's some more examples. Processes needed to exchange data flow between external data sources and sinks. So you're bringing in from a source to a sink, which is what we've been looking at so far. Or you might need to update a data store. Or you might need to represent the data from a database, pull it from a database itself or a data store. Or you might need to move it from one data store to another. So we have one data store that processes information, it sends it to another data store. So don't get confused with the terminology, it's more along the lines of the logic that's going on. So now you should be working on your analysis document, hopefully. And you're thinking about now the data flows and the processes that are going on in your system. And I usually take a few minutes to revisit this document, because we've finished, believe it or not, talking about entity relationships. Oops, this is Wednesday. And data flows. So let's take another quick look at this analysis document. Because I think if I keep showing it to you, it kind of lights a fire into some people. They go, oh, maybe I should start working on this. Because you don't want to wait until the very last week of the class to start looking at this stuff. All right, so at this particular point, you should have already decided what project you're going to be working on. If you're going to do it alone, if you're going to be in a team, you should probably be thinking about that. You should be working on your requirements. After you get done with the requirements, you're going to be starting to thinking about analysis. Half your team could still be putting together, well, actually not. You have to finish the requirements before you can start the analysis. You can kind of work on the analysis and design together, but requirements are pretty much the prerequisite for the project. So, oops, I had it up there, now it went away. I was looking at my table of contents. So I found out on page 25 is I've got that one memorized, is the requirements template, requirement specification. 47 is the analysis document that I've been talking about today in terms of, and this is the first two diagrams that you'll have to put together for it. Yeah, one of these days I'm going to learn how to skip to a page. Here we go, I'm getting close. The reading notes will show you how to document the process bubbles. I'll show you how to put that together. Okay, here we go. So on page 46 of the course notes, we've got the analysis document specification. Well, it's actually clearer up there than it is on my screen. It's good. Okay, I've already gone through the template already. If you've missed it, it's one of the previous lectures. But what I want to do is point out what I've been talking about today. And this is in the functional requirements section, section 2. And now you know what an entity relationship diagram is. Now you know what a data flow diagram is, hopefully, if you were here. So you're showing the entities involved with the entire scope of the project, not just the prototype. I do have students who just take, oh, we're not building it, we're just making the prototype. You're analyzing the whole system, the finished system that you're not going to build. You don't have to build it to analyze it. So think past the prototype. The database delivered with the prototype must be consistent if you're going to deliver a database. You don't have to deliver a database. A lot of people read this and they go, oh, I have to give a database with this? No, but it should be consistent if you are. You don't have to, though. Your entity descriptions in narrative format that clarify what each entity represents, and some who might not be familiar with a particular model. In terms of that, you could put together a legend, you could put together a list, or you could just create the diagram. You don't actually have to do anything for that. And I thought I had it written in here, but I don't. You want to have at least one. So you want to have attribute descriptions for each one of the attributes for each one of the entities, if you want. Should also include the data length, possible values, perhaps, edit criteria, unique data elements. If you just give me one diagram, you're fine. So for those of you who are listening to this, cut your work down in half. Just give me one entity relationship diagram. Or more, one or more. And for the data flow diagram, this is actually broken out into 2 separate sections. So it says data flow diagram, and then we see process descriptions. This is why I'm bringing up this example again, because we just talked about the data flow diagrams, and we have processes in those data flow diagrams. These are the processes I'm talking about. So if you number them in the diagram, it's easy to kind of come up with a dictionary of it right here in terms of your process descriptions. So you have to cover the entire project, must include a contextual level diagram and one or more lower level diagrams. I'm telling you, you don't actually have to do that, just give me one. If you give me more, if you follow this, you're actually creating the design. And you can go ahead and create the design if you want. When you're creating your one or so, it's going to be hard not to create a contextual level. You're going to do it naturally, because the data flow diagram is giving the context of the system. That's essentially what you're doing in terms of that concept. Or you can give me lower level ones. Must include primitive level process bubbles. Label your process bubbles for every process in the working prototype. So if you're going to create a prototype, you're going to give me processes that are going to actually prototype maybe in terms of your prototype, but I'll talk about prototyping as we get further down the road. Consistency of data between levels must be maintained. Call your data the same thing. So if you have a huge context diagram and you have smaller ones, call them the same thing so that the labeling is consistent. That's what that means. In terms of the process descriptions, every process in the data flow diagram must have a corresponding process description. Here's where I'm telling you that they can be processes that have to be described in any way that you want. They can be described in pseudocode, structured English. They can be described in words, in regular English. Your descriptions aren't essential. I mean, aren't really. They're not going to essentially affect your grading, I should say. In fact, sometimes the English words are better than pseudocode, as I mentioned earlier. Primitive level transformation descriptions should be documented in structured English pseudocode. This is what this means. Comparative mechanism for business logic. So it's unambiguous. And if you're wondering, well, where does this structured English pseudocode stuff come from? It's actually explained further up in the course notes. In fact, another thing you're going to find from the course notes if you download it and read it, is descriptions of how to create an entity relationship diagram, descriptions of how to create a data flow diagram as well. But if you understand what I gave you in the lecture, you don't necessarily have to go through and read all this stuff. Here's the relationships, data flows, and supplemental reading. Here's an example of process descriptions. Here's structured English. So you'll see all these terms defined in the reading, which is optional. So. And let me just continue a little bit under here. What we're going to do next week is talk a little bit more about diagramming techniques and move into the concept of design specifications and some of the other components that we're putting in to the analysis and design. You will actually put in one UML, so you'll put in, and I'll tell you more about that as we get closer. In fact, what a lot of students do is take the entity relationship diagram and translate it into an object diagram. It's 2 seconds, you got your UML diagram right there. But we covered what we were supposed to do today, which was the concept of the entity relationship and the concept of the data flow diagram, which was, for those of you who just came in, was lecture number 5 and 6, I believe. So next week we'll move on to lecture number 7, unless we have any questions from today. Oh, question, yes.
You have to include this ER diagrams and data flow diagrams as part of the analysis.
Yes. And how you're going to put this document together is you're going to use like Microsoft Word, and you're going to create the diagrams as images, and you're going to cut and paste them and put them in, or insert them in. So it's all together. Or if you're doing it by hand, you can actually give me separate pages. You don't have to do it on a computer.
What exactly is the object diagram?
I haven't talked about it yet. We're gonna talk about it. Yeah, it's coming up next. Object diagrams. I mentioned closely for those people who are familiar with UML. An object diagram is one of the simplest UML diagrams that is equivalent to an entity relationship diagram. It's just done in a UML notation instead of a structured analysis and design notation. It's relatively the same diagram though. And as I was mentioning before, just to clarify the point, the good thing about the entity relationship diagram, which is why it's used a lot, is that it does loosely translate into a lot of other diagrams, and it shows you a lot of the same things. Problem with the data flow diagram, and the reason why a lot of people don't like to use it, it doesn't translate. There's not a good UML equivalent to it. And why is that? Somebody can answer? No, maybe not. Because UML combines both processes and data. And the data is completely missing from a data flow diagram. You would think with the name of the data, with the name of the diagram, that's all you'd be talking about. But it's the processing of the data, not the data. That's the focus of that diagram. And you'd have to change the concept completely in order to get it to show both processes and data. And the reason why we have 2 diagrams is because they're both showing 2 different things. Processes are being shown in the data flow diagram. The entity relationship diagram is showing us data. So we have the 2 components separated out. We create 2 diagrams to give us the complete picture. If we take the entity relationship diagram, translate it into UML, UML or object orientation combines the both together in all of the diagrams. Then we have our choices. And what we're doing essentially is taking an entity relationship and adding processes to it. And when we add the processes, we come out with a class diagram or we come out with an object diagram. Object diagram, however, is kind of loose. It's kind of an entity relationship in a lot of different ways. It does translate quite well. But I'll talk about that in the next couple weeks. We'll go through some examples. Any other good questions? These are really good questions today. No? Then it's time for lunch. All right, I'll see you all next week.